Hello, this video is for the mechanics course. I'll talk about the Gimbal lock and Quaternions. By expanding the sequence of rotations given in the previous slide from n to cool, in ZYX Euler angles we get the following matrix of rotation. When choosing cosine beta equals 0 and sine beta equals plus or minus 1, we find that alpha and plus or minus gamma are indistinguishable. That is, the 2 degrees of freedom left degenerate into 1. Or, for example, this means that there's no local inverse around any point with beta equal pi over 2. Now I'll review the algebra of quaternions, which is a set of quadruples usually in the basis 1ijk. I'll sometimes write the last 3 components in bold, meaning a 3-dimensional vector, and the multiplication of quaternions is defined by the equation. Recall Euler formula. E to the mx equal cosine of x plus m sine of x, where m is any square root of -1. The exponential, cosine, and sine function of quaternions is defined using power series, and note that e to the x times e to the y is in general not equal to exponential x plus y when xy is not equal to yx. In particular, quaternions with vanishing real part and unitole vector part is a square root of -1. So the Euler formula holds and is of this form. By this fact, we know that quaternions is a division algebra, and in fact, the only non-commutative finite-dimensional real division algebra. Now, consider the function Rw that sends v to WVW inverse, where v is of real part 0 and w is a non-zero quaternion. After the calculations, we find that this linear function preserves the vanishing real part. When writing it in the form of a matrix, we find that this matrix is in fact in SO3. This can be checked by Rw transpose Rw equal identity. And note that W is a fixed point of Rw, so this is a rotation along the axis of W. Now we want to determine the angle by which the matrix rotates, so I changed it to the basis in W and 2 arbitrary vectors x and y, such that x, y, w are mutually orthogonal, and x cross y equals the normalized vector of w. Surprisingly, we find that this is a rotation by 2 theta, where theta is such that it satisfies this condition. So the conclusion is that when rotating the vector v along w by an angle of theta, it can be represented by a quaternion multiplication, e to the theta over 2w times v times e to the negative theta over 2w. Another important fact is that this function is invariant by changing w to a multiple of w. This means that we can always focus on unit vectors. But why is this important? Recall the phenomenon of Gimbal lock when using Euler angles. Implicit functions without local inverse exist. Now, when we view R as a function from theta and 3-dimensional unit vectors to SO3, this time it is exactly a homeomorphism, so local inverse or inverse exists. There's no occurrence of Gimbal lock. However, if you treat R as a function from quaternions to SO3, Gimbal lock can't be avoided. In the bottom of this slide is an example for your interest. Thank you for watching.